Alright, welcome to my lecture on the moment generating function. And we're also going to discuss transformations. Okay, so of particular interest, we're going to be looking at theorem 7.3.1, and it says this. So if we have two random variables with moment generating functions that are equal, then x and y are the same distribution, i.e. the density of x is equal to the density of y. Okay, and so this is going to be important theorem 7.3.1, but there's two more that we're going to use. So let me write those down as well. So theorem 7.3.2 says this. If we have a transformation and y is equal to x1 plus x2, then it says the moment generating function of y is equal to moment generating function of x1 times the moment generating function of x sub 2. Okay, and this is multiply. Okay. And if you were asked to prove this, you would just write m, the moment generating function of y, that's going to be equal to the expected value of e to the t times y. And then when you take the expectation of y, y has this representation. And that's equal to the expected value of e to the t times x1 times the expected value of t times x2. And then there's one more thing that we need to state, which is if independence of x1 and x2, this will be equal to the expected value of e to the t times x1 times the expected value of e to the t times x2, and that's the moment generating function of x1 times the moment generating function of x2 of t. And so when there's going to be one more statement in this moment generating function, then I need to assume if x1 and x2 are independent, we have that statement. Okay. And then we've proved the statement. Okay. So now, one more important thing is the following. It says this. So theorem 7.3.3 says this. If y is equal to alpha plus beta times x, then the moment generating is m sub y of t is equal to e to the alpha times t times mx of beta t, and that's multiply. Okay. Now let's do some examples. Okay. So let x1 be a normal distribution with mean 5 and variance of 2, i.e., so I can write all of this for x1 as x is normal with mu 5 sigma squared equal to 2. And instead of writing all of that out for x2, I'm just going to write that x2 is also normal with mean equal to -3 and sigma squared equal to +3. Okay. If y is equal to x1 plus x2, so here's going to be the question. What is the distribution One thing that I'm going to note here is that I'm going to assume x1 and x2 are independent. Okay. So first we're going to note on page 136, if z is normal with mean mu and variance sigma squared, then the moment generating function of z is going to be e to the mu t plus sigma squared times t squared over 2. So here the important thing to notice is that the variance of z is multiplied by t squared over 2, and that the mean is multiplied by t. Okay. So that is the general form of a moment generating function. Okay. So we're going to let y equal to x1 plus x2. By theorem 7.3.2, we're going to have that the moment generating function of y is going to be the moment generating function of x1 of t times by the moment generating function of x2 of t. Since x1 and x2 are normal, I know their moment generating function just by using this. Okay, so the moment generating function of x1 is going to be e. Okay, and we have to look at its mean and its variance. So x1 has mean 5, variance 2. E to the 5 times t plus 2 times t squared over 2. Now the moment generating function of x2 is going to be e, and it has a mean of -3 and a variance of 3. Okay, now I can combine these two to get e to the 2t, combining these two, plus 5 times t squared over 2, combining these two. Now this has the same form as the moment generating function described here. So by theorem 7.3.1, y has a normal distribution because it fits the normal distribution profile with mean equal to 2 and variance equal to 5. Okay, so that's an example of using theorem 7.3.1 and 7.3.2. Okay. Let's do a new example. So let x1 and x2 be independent, and we're going to have x1 Well, that's going to be normal. Mu equals 5, sigma variance equal to 2, and x2 is going to be normal with mu equal to -3 and variance sigma squared equal to +3 as before. But now I'm going to change my transformation. Y is going to be 2 times x1 minus x sub 2 plus 7. So now I'm going to use all the theorems that we used before. So now I'm going to use theorem 7.3.3. Okay, and I'm going to use it twice. I'm going to use it on this 2 and this -1, and I'm also going to use it on the 7. Okay. So first of all, I'm going to start with the moment generating function of y. Okay. Okay. The moment generating function of y is going to be 2x1 minus x2 plus 7 of t. Now the moment generating function says that I can break these up. So this is going to be the moment generating function of 2 times x1 of t times the moment generating function of minus x2 of t. Then for the 7 here, if we look at theorem 7.3.3, this becomes e to the 7t. Okay. Now, further applying theorem 7.3.3, I'm going to get the moment generating function of x1 composed with twice t times the moment generating function of x2 composed with -t times e to the 7t. Now, the moment generating function of x1, we have discussed it has the form of a normal distribution. So it's a normal distribution with mean of 5. So that's going to be 5. But instead of being multiplied by 2, I have to multiply it by 2t. Okay. Plus the variance of x1, which is going to be 2, times t squared, but instead of having t, I have 2t squared over 2 times the moment generating function of x2, which is going to be e to the -3, because that's its mean is -3, times a -t by composition, plus 3 times a -t squared over 2 times e to the 7t. Okay, and that's the moment generating function. So now we just combine. So this will be e to the 10t plus 3t plus 7t. So e to the 20 times t plus 2 times 2 squared will be 8 plus 3 is 11. And that's the moment generating function. This has the form, okay? This has the form of a normal. Okay. In fact, y is normal with mean 20 and variance 11. Okay, so that was your first example of moment generating functions and transformations. Okay, thank you.